Hey, and so begins Lecture 12. This covers Section 8.3 from the book, mainly conditional probability. But there'll also be some intersection and independence. I probably won't talk much about independence. So consider that we're going to understand and apply conditional probability. And we'll quickly do a probability tree. And let's not worry about this third one right now. And some of that has to do with just making sure that the pacings are correct for the exams. We can talk about that in our class. Anyways, conditional probability is how we update our thinking on an event occurring based upon new information. An example, if I were to ask you what is the probability that a person has received the COVID vaccine? And you're going, well, I might know a few people, but I don't really know that many. So, I don't know, 30%, maybe a little bit less. But if I told you that person was over the age of 80, you would go, wait a minute, that's not the right answer. It's much higher than that. Well, that's conditional probability. So, the probability given that the person is in their 80s is much different than the probability of the general population. So that's conditional probability, and that's what we're going to look at a little bit more today. Here's some other examples. What's the probability of drawing a heart given that the card is red? Well, it's 50%, so it's one half. If it's either a heart or a diamond. On the other hand, the probability of drawing a heart in general is 1/4. The probability of lung cancer given that the person smoked. It depends. Much higher then. So let's take a look at our sample space again. I might, we'll drop this off. Well, we're going to use this as our sample space, a standard DICE standard sample space that we have been using. Works pretty well for us, right? So let's consider the probability of rolling a 7. So that's this middle column here, given that the first roll, that the roll itself is odd. Well, how many events are odd? So we have, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's 18 possibilities that are odd, and 6 of those are 7s. So the probability that we roll a 7, given that it's odd, is 6 over 18. And this is a much higher probability than it is of rolling a 7, which is 6 over 36. So it's twice the probability. Let's look at it a little bit more closely. And we're going to show where some things are derived a little bit in just kind of a so-so way here. So the probability of A given B. What you'll notice, what we wrote is the probability of rolling a 7 given odd was equal to 6 over 18. But we also said that was the number that were basically 7 intersect odd, which happens to be all of 7, divided by the number that are odd. Okay, so this is our formula. So if we were to, let's just play around with this a little bit more. The probability of A given B, let's just make it more general, is equal to the probability, and is equal to n of A intersect B divided by n of B. This is absolutely true. I recommend that this is the way you kind of remember it most of the time. It'll work for you most of the time. But let's continue, because we can take this further. What you'll notice is you can convert, if you multiply this by 1. So now we take n A intersect B, and B, and multiply this by n of S, n of S. This equals So we divide this one by this and divide this one by this. And we'll end up with an A intersect B divided by NS divided by NB NS. And this, in fact, equals the probability of A intersect B divided by the probability of B. So the probability of A given B is equal to the number of elements in the intersection divided by the number of elements in B. We also have that the probability of A given B is equal to the probability of the intersection divided by the probability of B. So these are the two formula. These are the two ways you should try and work with this problem. You'll use both of them. Let's just run through an example. So we have a spinner. What is the probability? Whoops. Nope. We're not using a spinner yet. Sorry. Dice. What is the probability that only one of the dice is 2, given the total is less than 7? So the probability that one of the dice is 2, given the total is less than 7. Well, if we recall, this diagonal is 7, so we're looking at everything below this diagonal. There's two ways we can go about it, and we'll use both methods. Okay, we'll use both methods. So, oops, I'm almost out of paper on this in this folder. We'll have to redo that. So, let's do NB, and that is the number of events that are less than 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that equals 15. The number that are A intersect B. So the number in this group that have one of the dice is 2. That's 1, 2, 3, 4, 5, 6, 7. So there should be 7. Let's do that again. 1, 2, 3, 4, 5, 6, 7, which means I have a typo in what I have up above. I seem to do that regularly. And then we'll take the probability of A given B is equal to 7 divided by 15. Okay. Now let's also do it the other way, and then now we can calculate the probability of, what's the probability of the intersection? The probability of the intersection is equal to 7 divided by 36, and the probability of B is equal to 15 divided by 36. So then we have the probability of A given B is equal to 7 divided by 36 divided by 15 divided by 36, which is equal to, and I won't do it this way most of the time, 7 over 15. Okay? And I need to make sure that I correct this. I have a typo in there. Okay. I'm just going to grab some extra papers that I have because I just need a couple right now. Okay. Okay, here we go. These are just scrap papers. So. Now we're going to work with a pointer. This is example number 2. A pointer is spun on a circular spinner. The probabilities of the pointer landing on a given integer are indicated on this table. So they're indicated on the table. The integer and the probability. So what is the probability that the pointer lands on a prime number? So the probability prime is equal to, well, 1. I'm sorry, 1 is not a prime, so that would be 2, 3, 5. So 0.2 plus 0.1 plus 0.5, which is equal 0.3, which is equal to 0.6. Okay. What is the probability of the pointer landing on a prime number given that it landed on an odd number? So the probability of prime given odd. Well, what's the probability of odd? The probability of odd is 0.1 plus 0.1 plus 0.5. So that's equal to, again I did it, 0.3 here. Sorry about that. So that's total is 0.5. And the probability of odd intersect prime is equal to so the number 3 and the number 5. So 0.3, which is equal to 0.4. Okay, so we have a couple different things, and this is what we're interested in. So this is equal to, and I'm going to write it, probability of prime given odd is equal to their intersection, the probability of odd intersect prime, which is 0.4, divided by the probability of odd, which is 0.5. So that equals 0.8. I'll verify that. 0.4 divided by 0.5 is equal to 0.8. Okay. Now, I'm going to keep right on going here. The product rule. So the product rule is not a whole lot different than what we did. So if we look back at how we derived the equation, looking back at this, we can see that we have the probability of A given B is equal to the probability of probability of the intersection divided by the probability of B. Let's just do a little bit of algebra on here and multiply this back over. So then we have the probability of A given B times the probability of B is equal to the probability of A intersect B. Okay, we can do that, right? Now let's also say this is the probability of A given B, but there's also a probability of B given A. And the probability of B given A is equal to the intersection, because the order doesn't matter. I can change the order and it'll be, if I said the probability of B intersect A, it would be the exact same thing, divided by the probability of A. Right? Now let's multiply this back out, and we have the probability of B given A times the probability of A is equal to the probability of A intersect B. Notice, probability of A intersect B here, the probability of A intersect B here. That means these two are equal to each other. So the probability of A given B times the probability of B is equal to the probability of B given A times the probability of A. Each one of those is equal to the intersection. And that's exactly where this product rule comes from. So it's exactly what's indicated in this product rule. So the probability of the intersection is equal to the probability of A given B times the probability of B, which is the second equation, which is the second one here. And it's also equal to the probability of B given A times the probability of A. And they just changed the order from what I had it. But these are the same things. So this is the product rule. Now, what this allows us to do is to go up and down the probability tree. What is a probability tree? Well, we'll show you that in just a moment. But it allows us to find probabilities all over the place, which is really very, very useful. This is a probability tree. But we'll come back to that. I'm gonna stop this lecture now, and we'll do a second part to it, and that's when we'll talk about the probability tree. Thank you.